Hi, good morning. Today we are going to discuss one theorem. In the last class we have discussed one lemma. Just recall what is as our lemma. Let T be a linear operator on a finite dimensional space V. C1, C2, etc. Ck be distinctive characteristic values of T, and let Wi be the characteristic vectors associated with the characteristic value Ci. If W is equal to if W is equal to W1 plus W2 plus etc. plus WK, then our lemma says that dimension of W is equal to dimension of W1 plus dimension of W2 plus etc. plus dimension of WK. Okay, this is our theorem. Our lemma. Actually, what is dimension? W is W1 plus W2 plus etc. plus WK. Therefore, this theorem says that this lemma says that dimension of W1 plus etc. plus WK is equal to dimension of W1 plus dimension of W2 plus etc. plus dimension of WK. Okay. Now, moving to our theorem. What is our theorem? Let T be a linear operator on a finite dimensional space V, same as in our lemma. C1, C2, etc. Ck be distinct characteristic values of T. And Wi be the null space of T minus Ci. Actually, what is null space of T minus Ci? Null space of T minus Ci I is equal to set of all alpha belongs to V such that T minus Cii alpha is equal to 0. That is set of all alpha belongs to V such that T alpha minus Ci alpha, that is alpha equal to 0. That is set of all alpha belongs to V such that T alpha equal to Ci alpha. Now, what is this one? This is the characteristic space associated with the characteristic value Ci. So, our W is same as the characteristic space associated with the characteristic value Ci. Clear? Now, the theorem says that then the following these three conditions are equivalent. The first condition is T is diagonalizable. And the second condition is the characteristic polynomial for T is of this form. And dimension of Wi is equal to di, I varies from 1 to etc. k. And the last one, dimension of W1 plus dimension of W2 plus etc. plus dimension of WK equal to dimension of V. So, 1 implies 2, 2 implies 3 and 3 implies 1. Okay. So, T is diagonalizable implies clearly dimension of W1 plus dimension of W2 plus etc. plus dimension of WK equal to dimension of V. Okay. So moving to the proof, the first proof, T is diagonalizable implies characteristic polynomial will be of this form. This we have already discussed. Anyway, suppose T is a diagonalizable operator with diagonalizable, with the distinct characteristic value C1, C2, etc. Ck. Suppose C1 repeated D1 times, then we have already seen T of is of this form. Okay, this is the identity matrix of order D1 by D1. Okay, and where D1 is D2 etc. Dk is the multiplicity of the characteristic value C1, C2 etc. Ck. Now to prove 1 implies 2, we have matrix of T related to the basis is here we have given T is diagonalizable. So there exists T is diagonalizable means there exists a basis containing characteristic vectors of T. Okay, so suppose some T alpha 1 is equal to C1 alpha 1 and T alpha 2 equal to C2 C1 alpha 2. These are characteristic vectors. In there is a basis containing the vectors alpha 1, alpha 2, etc. Okay, so this C1 alpha 1 you can write as C1 alpha 1 plus 0 into alpha 2 plus etc. Then if we consider the matrix, then the matrix of the form is a diagonal matrix that we have already discussed in our previous classes. Okay, so this is our matrix. corresponding to the basis, because as T is diagonalizable, there exists a basis. All vectors of that basis is characteristic vectors. Therefore, the matrix of T related to that basis is of this form. Okay. Now, what is characteristic polynomial for T? Characteristic polynomial for T is determined x minus AI. Okay. So, what is determined? Sorry, this is determinant of xi minus a. Determinant of xi minus a. Determinant of xi minus a. Xi minus a means x minus c1, x minus c2, x minus c1 repeated d1 times, x minus c2, x minus c2, etc. repeated d2 times, x minus ck, x minus ck, etc. repeated dk time. Okay. So this is a diagonal matrix. Therefore, corresponding determinant is product of the diagonal elements. Okay. And that's it. This is the characteristic polynomial. Okay. So this is our first implication. One implies two. T is diagonal implies characteristic polynomial for T is of this form. Okay. One more thing is there. We have to prove this DI is same as dimension of WI. Okay. Now what is we have to prove dimension of WI equal to DI. Okay. Now, what is dimension of Wi? Dimension of Wi is the null space of E minus Cii. Okay. Therefore, Wj you can write null space of T minus Cji. To prove dimension of Wi equal to Di, it is enough to show that nullity of or dimension of this space is equal to Di. Okay. So, this is the proof of T minus Tji equal to Wi. Okay. We have T null space of T minus Tji is equal to Wj. Okay. So, what is the rank of T minus Tji? Number of, for a matrix, what is the rank? If you consider matrix in the row canonical form, rank is equal to number of non-zero rows of the canonical matrix. Okay. So, rank of a matrix T minus Tji is same as number of non-zero rows. Therefore, nullity of T minus Cji is the number of zero rows. Okay. We know that, suppose this is the matrix and matrix of order n. This is same as the dimension of the vector space. And we have row canonical form like this. And we know that rank nullity theorem, rank of T plus nullity of T is equal to dimension of V. Okay, in the case of matrix rank A, what is rank? Rank is row rank. Okay, plus nullity is equal to dimension B. If this represent number of non-zero rows, this represent total number of rows. Therefore, nullity represent number of zero rows. Okay, because sum is equal to dimension B. Therefore, nullity of T minus Cji is the number of zero rows. Okay. Now, what about number of zero rows? If you consider T minus matrix of T minus Cji, if we consider matrix of T minus Cji, that is matrix of A minus Cji, what happens? If you consider A minus C1i, what happens? These all become 0. Okay, and this become C2 minus C1, C3 minus C2 minus C1 repeated D2 times, and this become CK minus C1. Okay, so as CIs are distinct, C1 minus C2 not equal to 0, similarly C1 minus C3 not equal to 0, etc. C1 minus CK not equal to 0. So all these rows are non-zero, but the 0 rows are d1 times. Therefore, number of 0 rows is equal to d1. So, in this case, nullity of T minus Cji is same as number of 0 rows in A minus Cji, therefore which is equal to Dj. Okay, you can verify this. Okay, now 2 implies 3. What is 2? The characteristic polynomial for T is this one, and we have to prove this one. Okay, now what about the dimension of V? What about the degree of the characteristic polynomial? Degree of the characteristic polynomial is same as the dimension of the space. Okay, so this is our characteristic polynomial. Degree of the characteristic polynomial of T is equal to dimension of V. Therefore, here what about degree? D1 x raised to D1, here x raised to D2, here x raised to dk. So if you multiply all these things, the highest degree is x raised to D1 plus D2 plus etc plus dk. Therefore, what about the degree? D1 plus D2 plus etc plus dk equal to dimension of V. And this implies dimension of V equal to each dj is same as dimension of wj. Therefore, dimension of w1 plus dimension of w2 plus etc plus dimension of wk. So we have dimension of V is equal to this one. Now the last one, and this is one of the most important result. We are using this result in our next class. Okay. Suppose dimension of W1 plus dimension of W2 plus etc. plus dimension of WK equal to dimension of V, and we have to prove that T is diagonalizable. Okay. To prove T is diagonalizable, what we have to prove? We have to prove there exists a basis consisting of characteristic vectors. Okay. So by lemma, what we have? Dimension of W1 plus etc. plus dimension of WK equal to dimension of W, where W is W1 plus W2 plus etc. plus WK. So we have this result. But here right hand side is dimension of V. Here right hand side is dimension of W1 plus etc. plus WK. So what we get? Dimension of W1 plus etc. plus WK equal to dimension of V. Okay. Now we know that Wi's are subset of V. Wi's are characteristic space associated with the characteristic value Ci. Clearly Wi is subset of V, and we know that W1 plus W2 plus etc. plus Wk is also a subset of V. But here we get the dimension are equal. Therefore both space are equal. Therefore V is equal to dimension W1 plus W2 plus etc. plus Wk. So in the proof of lemma, we have already proved if W is equal to W1 plus W2 plus etc. plus WK, then B1, B2, etc. BK is a basis for W1, W2, etc. plus WK. Then this set form a basis for W. That we have already proved. So here we get this is a W1 plus W2 plus etc. plus WK equal to V. Therefore, using above lemma, B equal to B1, B2, etc. Bk, where Bi is a basis for Wi, form a basis for V. Okay. So, what about Bi? Bi is a basis for Wi. Therefore, clearly Bi is a subset of Wi. What about Wi? Wi is the set of all characteristic vectors associated with the characteristic value Ci. So all elements of these BIs are characteristic vectors associated with the value Ci. Okay. So what about for any alpha in W, T alpha is equal to Ci alpha. Okay. So B1 contains characteristic vectors associated with the characteristic value Ci. C1, B2 contains characteristic vectors associated with the characteristic value C2, etc. Bk contains characteristic vectors associated with the characteristic value Ck. That means all elements of this set are characteristic vectors. Okay. Thus, V has a basis containing all characteristic vectors of T. Okay. This implies T is diagonalizable. Okay. V has a basis containing all consisting of the characteristic vectors of T. This implies T is diagonalizable. Okay. Hope everything is clear. That's all for today's class. Okay.